Okay, hello everyone. Welcome to the second part of tutorial 6. Let's start with question number 8. You are given here arbitrary distinct points in two-dimensional planes. Each point will have an x coordinate and a y coordinate, and the points are having integer coordinates, right? So they are arbitrary points except that they are distinct. So I'm denoting the points, their respective coordinates as x1 y1, x2 y2, x3 y3, x4 y4, and x5 y5. And our goal is to show that irrespective of the way these 5 points are chosen arbitrarily, there always exists a pair of points such that if you consider the midpoint of the line joining those 2 points, it has integer coordinates. So just to recap, if you have 2 points, a point with coordinates a1 comma b1 and another point with coordinates a2 comma b2, then the midpoint of the line joining these 2 points is given by this formula, right? And we want to apply here pigeon-hole principle. So remember, for pigeon-hole principle, we have to identify the set of pigeons and the holes here, and then the mapping which relate the pigeon and the holes. So let's do that. So consider the set of 5 points, the arbitrary 5 points, right? Remember, they are arbitrary 5 points except that they are all distinct and they have integer coordinates. And I'm trying to map these points depending upon what's the nature of their x coordinate and y coordinate, right? So depending upon whether the x coordinate is even or x coordinate odd, or whether the y coordinate is odd or the y coordinate is even, I have 4 possible combinations. And my function f maps these 5 points to the corresponding pair. Say if x1 is odd and y1 is even, then I will say that f of x1 comma y1 is odd comma even and so on, right? That's a mapping here. Okay, so now it follows from the pigeon-hole principle that we have now 5 items here in the set A and 4 items in the set B. Then there always exists a pair of points among these 5 points, say xi comma yi and xj comma yj, such that both of them are mapped to the same ordered pair, right? So it could be any of those, any 2 out of those 5 points. It could be the first 2 points, it could be the last 2 points, it could be the third point or the fourth point and so on. We don't know. It depends upon the exact 5 points that we choose. So what we do here is we apply our principle without loss of generality principle. So without loss of generality, assume that out those 2 points which are guaranteed to be mapped to the same ordered pair are the first 2 points, right? So say x1 comma y1 and x2 comma y2 be the 2 points such that the corresponding f output of the f function for these points are the same. Now we want to inspect what happens to the midpoint of the line joining these 2 points A and B. Okay. So as per the formula, the midpoint of the lines joining these 2 points A and B will be x1 plus x2 over 2, y1 plus y2 over 2. Okay. And since both the points A and B are mapped to the same ordered pair, right? So for instance, it could be the case that both x1 as well as x2 are odd, or it could be the case that both x1 as well as x2 are even. So irrespective of the case, x1 plus x2 will always be divisible by 2. If both of them are even, definitely the sum of 2 even quantities divided by is divisible by 2. Whereas if both of them are odd, then also the sum of 2 odd quantities is divisible by 2. Right? And as per our assumption, it's not the case that x1 is odd and x2 is even. That's not the case because we are considering the case when the output of the f function on these 2 points A and B are same. Right? In the same way, we can't have the case where x1 is even and x2 is odd because that's not the property of the point A and B. Due to exactly the same reason, the type of y1 and y2 coordinates are the same. Either they are both odd or both of them are even. Right? And again, in this case, it's easy to see that y1 plus y2 will be divisible by 2. And that shows that this statement is a correct statement. Okay, right. So let's go to question number 9. Here you are given the following. You are choosing 5 uh, integers from the set 1 to 8 arbitrarily, right? I say arbitrarily. Our goal is to show, irrespective of the way you choose those 5 points, there always exists at least one pair of integers among those chosen 5 integers whose sum is 9, right? So for instance, if you pick say 1, 2, and then say you want to avoid the sum 9, so you don't pick 6 because otherwise the statement is true. So you say you pick 5, and then 5 to 7, 8, and then you pick say 4. If you pick 4, then 5 plus 4 is 9. If you don't pick 4, if you pick say 3 also, then also you have 5 plus 3 plus 1, 9, and so sorry, so you have to show about the pair of integers, right? So say you pick 1, 2, and 5, okay, and then if you pick 3, then you still don't have any pair of integers whose sum is 9, but as soon as you pick the 4th point, you will end up picking. So if you pick 4 as the 5th number, then you have 5 and 4, which is summing up to 9. If you pick 6 as the 5th number, then you have 3 and 6 summing up to 9. If you pick 7 as the 5th number, then you have 7 and 2 summing up to 9. If you pick 8 as the 5th number, then you have 1 and 8 summing up to 9, and so on. Right? So you can verify this by an example, but we want to prove it irrespective of the 5 numbers that we are going to pick. So one way of proving this is that you take all possible 8 choose 5 ways of picking 5 numbers, and for each of those combinations you show that this statement is true, but that will be an overkill because this is a relatively large value, right? Instead, we will apply the pigeon-hole principle, and again for applying the pigeon-hole principle we have to identify the pigeons and the holes here and the mapping. So by pigeons, here are the 5 integers among the numbers 1 to 8 that I am picking arbitrarily, and my holes are the ordered pairs, namely ordered pairs of integers, distinct integers in the set 1 to 8 whose sum will give you 9. So you have either the ordered pair 1, 8, or the ordered pair 2, 7, or the ordered pair 3, 6, or the ordered pair 4, 5, and you don't have any other ordered pair where from the set 1 to 8 summing up to 9, right? And my function f basically maps these xi values to the corresponding ordered pair. Depending upon whether x1 is 1 or 8, I will say that f of x1 is either 1, 8, or if x1 takes either the value 2 or the value 7, then I will say f of x1 is 2, 7, or if my x1 is either 3 or 6, then I will say that f of x1 is 3, 6, or if my x1 is either 4 or x1 is either 5, then I will say that f of x1 is 4, 5. That's the interpretation for my mapping f. Now, it follows simply from Pigeon-hole principle that there always exists a pair or two values out of the 5 numbers, say xi, xj, such that f of xi and f of xj are same. It could be, say, the first two values, the last two values, the second or the third value, the third or the fourth value, or the first value or the fifth value. It could be any two values out of those 5 numbers, right? We don't know which one. So again, without loss of generality, suppose both of them got mapped to 1, 8. We don't know what is the identity of xi or xj, and we don't know the corresponding mapping as well. It could be either 1, 8, 2, 7, 3, 6, or 4, 5. So without loss of generality, that means whatever reasoning we are giving here for the case where f of xi is equal to f of xj equal to 1, 8 hold, the same argument will hold even if f of xi is same as f of xj is equal to say 2, 7. The same reasoning will hold symmetrically for that case as well, symmetrically for the case when it is 4, 5, symmetrically for the case when it is 3, 6, and so on. So that's why we don't consider the remaining 3 cases, we just consider the case when f of xi and f of xj is 1, 8. If that is the case, then since your xi and xj are distinct, okay, and they got mapped to 1 comma 8, that means either xi is 1 and xj is 8, or xi is 8 and xj is 1. Irrespective of the case, the sum of xi and xj is 9. So now you can see that even without enumerating all possible C8 choose 5 arrangements or combinations of picking 5 numbers out of these 8 numbers, we ended up arguing in a very simple fashion that our statement is true using pigeonhole principle, which shows the power of this proof strategy, okay, or counting mechanism basically. Question 10, we want to prove a universally quantified statement. Namely, we want to prove that you take any integer n, there is always a multiple of n which has only the digits zeros and ones in its decimal expansion. Right, so before going into the proof, if you want to take few examples, say n is equal to 1, then I always have the number 1 which is a multiple of 1 and which has only the digit 1 in its decimal expansion. Remember, it's not mandatory that you have both zeros as well as 1 in the decimal expansion. Okay. The only restriction is we have to show that in the decimal expansion you only have either the digits zeros or ones. If you take n equal to 2, then I can take the number 10, which is a multiple of 2 and which has only ones and zeros in its decimal expansion. If I take n equal to 3, then I can take the number 111, which has only the digits 111 in its decimal expansion and which is divisible by 3. So at least for example, by taking few examples, we found that the statement is true, but this is a universally quantified statement and we can't prove a universally quantified statement just showing examples for few cases. So we have to get the proof for arbitrary n. Again, we are going to apply here pigeonhole principle. What we do is we do the following. So let me define few decimal numbers here. I define the first decimal number to be 1. I define second decimal number as 11, the ith decimal number as a decimal number consisting of I number of ones, and the n plus 1th decimal number which has the digit 1 n plus 1 number of times. Okay. Now let me define another set of values. So my value r of 1 is the remainder which I obtained by dividing a1 by n. Similarly, I define R2 to be the remainder obtained by dividing A2 by N. I define Ri to be the remainder obtained by dividing Ai by N. And in the same way, I define R of n plus 1 as the remainder obtained by dividing An plus 1 by N. Now, what can I say about these remainders? Right? It's easy to see that these remainders belong to the set 0 to n minus 1 because of the simple fact that you divide any number, right, by n, the only possible remainders could be 0 if it is completely divisible by n, or the remainders could be 1, 2 or n minus 1. Now, you have to apply the pigeonhole principle. So, my pigeons are the numbers a1 to a of n plus 1 that I have constructed here. And my holes are basically the remainders which I can obtain by dividing these n plus 1 numbers by n, and I have n possible remainders, and my function f map the numbers to the corresponding remainder which I obtained by dividing that number by n. So you have more number of numbers and less number of remainders, so it follows from the pigeonhole principle that you always have a pair of numbers ai and aj out of this n plus 1 numbers, which gives you the same remainder if you divide ai and aj by n. I don't know the remainder. It could be either r1, it could be either r2, it could be either r3, right? The remainder could be either 0, or the remainder could be either 1, or the remainder could be n minus 1. I don't know what are the individual remainders that ai and aj are going to give on dividing by n, but what I can know is that they are giving me the same remainder. And again, without loss of generality, assume that ai is occurring before aj in my sequencing here. Now, what can I say about this number aj minus ai, right? So aj will be a number which has j number of ones, and ai is another number which has I number of ones. Both of them gives me the same remainder on dividing by n. So if I take aj minus ai, right? Sorry, it should be. If I take aj minus ai, then this will be a decimal number which will have trailing zeros, and then at the leading positions you will have the ones. That means it's a decimal number which has only the characters ones and zeros. But what can you say about its divisibility by n? This number will be divisible completely by n because aj gives you the same remainder, say r. So I can say aj is some qj times n plus the remainder r, and ai also gives me the same remainder r, so I can write ai as some qi times n plus r. Then if I take aj minus ai, the effect of r and r cancels out, and I get that it's completely now a multiple of n. So I showed you constructively here that irrespective of what is your n, I can always give you a number which is divisible by n and which has only ones and zeros in its decimal expansion. Okay, right. Now let's go to question number 11, which is really a very interesting question. Here we want to show the following, that you take any sequence of n square plus 1 distinct real numbers, right? They are arbitrary real numbers, maybe positive, negative, in any order you take them, right? The only condition is that they have to be distinct. Then the claim is that irrespective of the way you pick, or irrespective of the n square plus 1 real numbers that you have in your sequence, you always have a subsequence of length n plus 1, right, which is either strictly increasing or strictly decreasing. First of all, okay, what is a strictly increasing sequence? A sequence of the form a1, a2, and so on, where a1 is strictly less than a2, a2 is strictly less than a3, and so on. Whereas if I have a sequence of the form a1, a2, a3, and so on, where the sequence is decreasing continuously and there is no equality allowed, and it's a strictly decreasing sequence. Now what does a subsequence means? A subsequence means here that the values may not be consecutive. That means I am allowed to miss few numbers. Okay, in the sense, say I take a sequence a simple sequence 1 3 0 minus 5 2 8 and so on. Then I can choose to pick 1 and then exclude 3 and 0 and minus 5. So this is a valid subsequence. This is a subsequence. Okay. In the same way, I can pick a subsequence saying 3, 2, and 8. That means I skip 0, I skip minus 5. Right. So what this question basically says is that irrespective of the way your n square plus 1 distinct real numbers are chosen, you always have a subsequence. By that I mean that you have a set of n plus 1 values going from left to right, but need not be in consecutive locations, right? Some of the locations might be skipped, but the number of values are n plus 1 such that if you view those n plus 1 values, they are either strictly increasing or strictly decreasing. That's what we have to prove. Again, if you want to convince yourself whether this is indeed a true statement or not, you can take some concrete values of n, try to draw any possible sequence of n square plus 1 for that value of n, and you can verify that this statement is true. But now we want to prove it for any arbitrary sequence. Okay, how do we do that? So let the arbitrary sequence of n square plus 1 distinct real numbers be denoted by a1 to a of n square plus 1, Okay, why I am taking arbitrary here? Because I want to prove this statement for every sequence, right? So this is a universally quantified statement, and to prove a universally quantified statement, I can use the universal generalization principle by proving that a statement is true for some arbitrary element of the domain. My domain here is the set of all possible uh, sequences of n square plus 1 distinct real numbers. I am just taking one candidate element from that domain arbitrarily. Okay, I don't know the exact values of a1, ai, aj, a of n square plus 1. What I will do is, to prove this statement, I will use pigeonhole principle along with proof by contradiction. So let me first define two values. I define this capital I value with index small I and the capital D value with index I. So what is this I of I denotes? It's the length of the longest increasing subsequence starting at AI, right? So AI will have some value depending upon what is the arbitrary sequence, and it will have some various possible increasing subsequences starting at AI. One might be of length 1. A trivial increasing subsequence starting at AI is the value AI itself. That's the subsequence of length 1. But I might be having a subsequence of, say, length 2, which is strictly increasing and starting at AI. I might have a subsequent of length 3 starting at AI, and so on. So whatever is the length of the longest increasing subsequence starting at AI, I am denoting it by I of I. In the same way, I might have several strictly decreasing sequences starting at AI. In fact, the sequence AI itself is a subsequence of length 1, which is strictly decreasing. Okay, but I might be having a subsequence of higher length, which is strictly decreasing and starting at AI. So the length of the longest decreasing subsequence starting at AI, I am denoting it at D of I. So that means with A of 1, I have associated the values I1 and D1. With A2, I would have associated the value I2, D2, and similarly with A of I would have associated the value II and DI. With AJ, I would have associated the value IJ, DJ, and with A of n square plus 1, I would have associated the value I of n square plus 1 and D of n square 1 plus 1. Okay, it's easy to see that I of n square plus 1 will be 1, D of n square plus 1 is 1. Okay, because I have only one subsequence starting at A of n square plus 1, namely the value a n square plus 1 itself. It is both an increasing subsequence starting at a n square plus 1, as well as it is a decreasing subsequence starting at a n square plus 1, because there is nothing after the number a of n square plus 1. Okay, now what is my goal? The question basically asks me to show that there always exists some I or some value a of I such that there either exists an increasing subsequence of length n plus 1, that means I of I is greater than equal to n plus 1, or there is a decreasing subsequence of length n plus 1, that means di is n plus 1. I have to show the existence of one such number ai in this subsequence. I prove that by assuming a contradiction. So assume that the statement is false, and that means for each ai in the sequence, the value I of I is at most n. That means you take any number in the sequence, the maximum length increasing subsequence is of length n, and the maximum length decreasing subsequence is also of length n. Okay, what does that mean? That means if I try to pair all I of I and D of I pairs, then they can take the values in the range 1, 1 to n, n, namely n square possible pairs. Okay, these are the possible values of II, Di pairs. But how many numbers I have in the sequence? I have n square plus 1 values in the sequence that I have chosen. That means I have more pigeons and less holes. What does that mean? So by PHP here I mean pigeonhole principle. So pigeonhole principle guarantees me that you definitely have a pair of values here, say a of I and a of j, right, such that your I of I and I of j are same. That means the length of the longest increasing subsequence starting at ai is the same as the length of the longest increasing subsequence starting at aj, and in the same way the length of the longest decreasing subsequence starting at di is same as the length of the longest decreasing subsequence starting at dj. And as per my assumption, ii, ij, di, dj are all upper bounded by n because I assumed a contradiction. Now, how do I arrive at a contradiction here? So I assumed the contrary to the statement what I wanted to prove, but I have to arrive at a contradiction. So there could be two possible cases with respect to the magnitude of ai and aj. The first case is that the value of ai, the magnitude of ai is less than aj. Not magnitude, means value wise ai is less than aj. If that is the case, then what I can say is the following. I can say that you take the increasing subsequence starting at aj. Okay. What is its length? Its length is I of j. And if I put the value a of I at the beginning of that subsequence, then that gives me now a new increasing subsequence, right? Starting at ai and of length I of I plus 1. But that goes against the assumption that the length of the longest subsequence starting at ai was I of I, right? So that's how I arrive at a contradiction. On the other hand, if I take the case when ai is greater than aj, then I have to just give a symmetric argument. What I can say is the following. I know that there is a decreasing subsequence starting at aj and its length is d of j. My claim is that if you take that subsequence and put an ai at the beginning, then that now gives me a new decreasing subsequence starting at a of I, and the length of this new decreasing subsequence is di plus 1, which now goes against the assumption that the length of the longest decreasing subsequence starting at a of I was di. That means in both the cases I arrived at a contradiction, and that shows that whatever I assumed here, that means the value of each I of I and each d of I was upper bounded by n, is incorrect. That means there is at least one a of I where either I of I is greater than n or d of I is greater than n. I don't know what exactly is that ai, right? So I gave you a non-constructive proof here, but I argued that the existence of such ai is guaranteed. Now let's go to question 12. In this question, we want to show the following. You are arbitrarily picking 9 people who in the age group of 18 to 58. Okay, that means the minimum age that is allowed is 18, the maximum age is allowed 58. Now we want to prove that irrespective of what exactly are their ages, as long as they are in the range 18 to 58, it is always possible to choose two disjoint groups of people out of these 9 people whose sum of ages is the same. Again, we will do this by pigeon-hole principle. So the first thing is, since we want to argue about a non-empty set of people, because when I want to consider the age of the people, there have to be people in the group. So I have to focus on non-empty subsets. So if I have 9 people, then the number of non-empty groups that I can form out of those 9 people need not be disjoint, is 511. And now what I can say about the range of the sum of ages in these 511 subsets. The minimum age that a subset, if I consider the minimum sum of ages possible in a group, it could be 18. This is possible only when I have a group of just consisting of one person, and that person has age 80. That's a maximum possible sum. That's a minimum possible sum. Whereas the maximum possible sum can occur when in my group I have all the 9 people, person 1, person 2 and up to person 9, and each of them has age 58. That's the maximum possible value of sum of the ages in a group of in a group picked from 9 people, right? That means the range of possible sums here is 505. So now let's apply the pigeonhole principle. My pigeons are the various possible non-empty set of people that I can form out of this group of 9 people. So I have 511 possible subsets, and my holes are the range of sum of ages. That means what can be the sum of ages if I consider various possible subsets, given that the ages could be in the range 18 to 58. So I have more pigeons than holes. So by pigeonhole principle, I can say that there always exists a pair of group Si and Sj such that the sum of the ages of the people in Si and Sj are the same. But my question wants me to show that the group should be disjoint. So how do I argue that I can always form disjoint groups of people out of this S of I and S of j? Well, if they are already disjoint, then I have showed the existence of two groups having the same sum of ages. But if the sets Si and Sj are not same, if they have some common people, just remove the common people from both the set Si as well as Sj, right? Both the set of common people, the common people in the set Si and Sj were contributing the same amount to the sum of the ages in the set Si as well as in the set Sj. So if I remove those common people, the same amount will be removed from the sum of ages in Si and Sj, and now where I will get two disjoint groups of people having the same sum of ages. Okay. In question 13, you are given the set A consisting of the numbers 1 to 2n, and we want to show that if I pick an arbitrary subset B consisting of n plus 1 elements from the set A, then irrespective of the subset, there always exists a pair of values such that one divides the other. Okay, and this is again a very interesting question. So for applying the pigeonhole principle, what I do is I divide this set A into two disjoint subsets, namely the subsets consisting of the odd values and a subset consisting of the even values. Both of them will have the cardinality n. Okay. Now my claim is the following. You take any value in the set A, it has a unique factorization of the form that you have some power of 2 multiplied by the remaining value, where the remaining value will be a number, specifically an odd number in the subset 1 to n minus 1 to 2 of n minus 1. For example, if your number x that you are taking in the set A is already an odd number, then I can write it in the form 2 power 0 into x. So in this case, my A will be 0 and my x will be x itself, right? So my statement is true. Whereas if your x would have been say 6, then 6 can be written as 2 into 3. So you have 2 power 1 times an odd value. If your x is say 10, then you can write it as 2 power 1 into 5. If your x is say 20, then you can write it as 2 power 2 into 5, right? So you can see that irrespective of the case, whether your x is odd or even, this claim is always true. So for x being odd, the statement is always true, but the statement is true even for a general x which is even, because for such x where x is either 2, 4 or 2 of n, I can express it in the form 2 power some positive exponent e1 followed by the remaining values, and this is because of the fundamental theorem of arithmetic that every integer has a unique prime factorization. The claim is that if I consider the remaining prime factorization here, then that will be an odd value, and that odd value will be in the set capital O here, and it's easy to verify that. So that means this claim is true. Now based on this claim, I have to apply the pigeonhole principle. For applying the pigeonhole principle, I do the following. Let P be the arbitrary set of n plus 1 values that I have chosen, and I map those arbitrary chosen values to the leftover value in its unique factorization that this claim guarantees, right? So A1 will be written in the form of some 2 power x1 into B. So A1 will be mapped to this B1, sorry. A2 will be written in the form of some 2 power x2 into leftover thing. That leftover thing is an odd number in the set capital O. So A2 will be mapped to B2 and so on. That's the mapping F here, right? Now what is the set O, cardinality of set O? That is n. That means my number of holes is n. But the number of pigeons is n plus 1. That means by pigeonhole principle, it is guaranteed that there exists a pair of values ai and aj out of this n plus 1 values, right? Where a of I is some 2 power xi into some leftover thing, which is an odd value, and aj is some 2 power xj multiplied by the same leftover value b. Okay, I don't know the exact value of that leftover odd value b, but that leftover odd value b will be the same. That's a guarantee. Okay, and exponents xi and xj, they will be positive, and they may or may not be positive. But they may or may not be same as they may not be same. They are not same actually, because I am considering the distinct values ai and aj here. So xi and xj are definitely not same, but what is guaranteed is that the leftover odd value here that is there as per this unique factorization claim will be the same. Now I have two possible cases. If ai is greater than aj, then clearly aj divides ai, because if I divide aj by ai, then the effect of b and b goes out, and the exponent xi is greater than exponent xj. So whatever is left over, that will be the quotient, right? And the remainder will be 0. Whereas if aj is greater than ai, then again the effect of b and b vanishes, and 2 power xj over 2 power xi, that will give you 0 remainder. Okay. So irrespective of the case, my statement is correct. Now let's go to the last question. Here we want to find out how many solutions are there for this equation where there is no restriction on xi, where there are various possible restrictions on xi. So in part A, we have the restriction that each xi has to be greater than 1. So you can imagine that you are given here bills of type x1, bills of type x2, and bills of type x6. We have to pick total 29 bills with the restriction that you have to definitely pick at least more than one bill of each type. That's the interpretation of this first restriction. That means I have to compulsorily pick 2 items of type x1, x2, x6. That means I had already picked 12 items compulsorily. That means now I am left over with the problem of picking 17 bills in total out of these 6 different bill types where there are no restrictions. And remember, as per the formula for the number of combinations with repetitions, this is the answer. In part B, the restriction is this. Again, if I interpret this restriction, that means I have to definitely include 1 bill of type x1, 2 bills of type x2, 3 bills of type x3, 4 bills of type x4, 6 bills of type x5, and 6 bills of type x6, definitely. That means I have already picked 22 bills of various types. That means now my goal was to pick 29 bills, 22 definitely I have already picked. So I am left over with the problem of picking 7 bills, where those 7 bills can be of type x1, x2, x6 in any possible order, no restrictions. So again, from the formula for number of R combinations with repetition, this will be the answer. In part C, the restriction is that x1 should be less than equal to 5. So, okay, so what we do here is the following. We first find out the number of solutions where there is no restriction. Okay, that means x1 may be 0 as well. In those solutions are also included in this value, this quantity, right? And now I try to find out those solutions where this condition, namely x1 less than equal to 5, is violated. That means I find the number of solutions where x1 is greater than equal to 6. That means definitely I have to pick 6 bills of type x1, which further implies that now I am interested to pick the remaining 23 bills without putting any restriction that how many bills of different types I have to choose. The number of solutions for this case will be this. But this is not what we want. We want to find out the number of solutions which do not have this condition. So what I do, I subtract this value from the set of, or from the number of solutions that I have without any restriction, and that will give me the answer. The last part here, my restrictions are x1 should be less than 8 and x2 should be greater than 8. Let's first try to find out the number of solutions where x2 is greater than equal to 9. That means just try to satisfy the second restriction here. The number of solutions will be this, because if x2 is greater than equal to 9, that means 9 bills of type x2 definitely have to be chosen. That means now I am left with the problem of picking 20 bills from bills of 6 types without any restrictions. And now let's try to find out the number of solutions where this first restriction is violated, namely x1 is greater than equal to 8 and x2 is greater than equal to 9. Okay, so what basically I am trying to do is the set A that I have defined here, it has all those solutions where x1 is less than 8 as well as x1 is greater than 8. So I am trying to take out those solutions where x1 is greater than equal to 8 from this set A. I am denoting that set as B, and the cardinality of the set B is this, because if I am supposed to satisfy x1 greater than equal to 8 and x2 greater than equal to 9, that means I have already picked 17 bills. My goal will be now to pick 12 more bills from bills of 6 types without any restrictions. This will be the number of ways or the number of solutions. And as I said, from the interpretation of the set A and B, the required number of solutions is the difference of these two cardinalities, which we can easily find out. So with that, we finish our tutorial number 6. Thank you.